So in this video, we will go over multiple regression. So a multiple regression is pretty similar to a single regression. This should say single, but I guess simple works here too. So a simple single regression uses one explanatory variable, while the multiple regression uses more than one explanatory variable. Okay, so in the example we used before, if we're trying to find the variables of food expenditure, we can use income and price. So previously we just used income, but in a multiple regression, we can use different variables. So we include price, and then we'll use different coefficients for each variable. So these are so for beta 2, change of food expenditure over income. The important part is when price is held constant. And then same for finding the slope of food expenditure in relation to price. So when we're measuring errors, we found out how to do that in the simple linear regression just by using the qualities of the sum of squared errors. And actually, in the multiple regression, we would do pretty much the same thing. So it's still determined by the difference of the y-axis. In this case, it's food expenditure, but this time the graph becomes three-dimensional. So I try to draw my best out here, where the price and income are going in different three-dimensional axes. And since we have multiple explanatory variables, we should have the plots being not necessarily two-dimensional, but being in a 3D plane. And then for the multiple regression assumptions, it should be pretty similar to the singular regression. So linearity, expectation of errors equals 0, homoscedasticity, no correlation, and then values of x are not random. The main difference is that there's a sixth assumption for the multiple regression, which is normality assumption. So it is important for a multiple regression to be normally distributed. And then so a consequence of that is that the errors are also normally distributed. And then so the least square minimization, we'll do the same thing, except we'll try to minimize based on multiple variables, so beta 2 and beta 3. So if we do that, logically speaking, we would usually get a lower sum of squared error because we're using multiple explanatory variables to minimize the least squared. So a quick example is with this equation right here. So 50 plus 10 times income minus 5 times price. If in our specific case that our income is 100 and our price is 50, how much would our food expenditure be? So as you might guess, we can just plug this in. So 50 plus 10, 100 minus 5 times 50. So this is 1,000, 1,050, and then minus 250, so 800, I believe. 1,050, 250, yeah, 800. Okay. So our unbiased estimate for the variance is the sum of squared errors divided by the degrees of freedom. I guess what distinguishes the linear regression for the sum of squared errors is that when we're subtracting by the degrees of freedom, we need to remember that the degrees of freedom is more than 1, or the k here is more than 1. So usually when we find the degrees of freedom by subtracting from the sample size, we're going to have to subtract by more than 1 usually. So in this case, we have 2, k equals 2. So we're going to have to do, like, if our sample size is 50, then the degrees of freedom will be 48. So under the multiple regression of 1 to 5 assumptions, we can conclude that the estimation is blue, or the best linear unbiased estimator. Okay, so you can kind of see that a lot of things I just went over are pretty similar to a simple linear regression. Let's try to measure the correlation between the explanatory variables, so beta squared and beta 2 and beta 3. And so this is something that you can't really do in a single linear regression because we have only one type of explanatory variable. So when we're measuring the correlation between these two explanatory variables, we get the variance of the beta 2, which is this function given here. So similar to what we measured before, except we have the correlation variable here. So with a little more inspection, you would see that the larger our correlation between our explanatory variables is, then this part becomes smaller, this whole fraction becomes bigger, and then the variance of beta 2 also becomes bigger. And so in conclusion, that makes it, if our explanatory variables are more correlated, that means our beta 2 becomes more imprecise. So usually we don't want our explanatory variables to be correlated. As you see here, if the correlation is close to 1, then by this estimation, it's not going to quite literally be infinity, but it's kind of a symbol for we can't really calculate it, because as this part goes smaller, then this whole fraction becomes infinitely bigger. It'll never actually be 1, because if it's two different variables, the only way it can be like exactly correlated is if they're the actual same variables. But it's kind of just saying that we don't want it to be similar either, because then we won't be able to efficiently calculate the correlation or the regression function if we have similar explanatory variables. Okay. We also want to avoid collinearity between binary variables. Let's say that we want to, we're given this function right here where we have beta 2 male and plus beta 3 female. This is an example of perfect collinearity because male and female are binary of each other, if that makes any sense. They have to be 1 and 0 if you add up their probability. And so what this results in is an identification problem where the formula will look like this. So the beta 1 belongs to both male and female because the probability of male or female has to equal 1. And we don't want that. So I guess in this video, the main summary is that mostly the multiple regression is pretty similar to simple linear regression, but we have to avoid the problem of multi-collinearity, as we can see like in these equations here. All right, that's pretty much it for now. In the next video, I'll go over more concepts on multiple regression.